All right, so here's my grand plan for today. I thought we would talk about the solution to the homework you just turned in, and I will post this solution right after class, but I'm happy to basically go through it as driven by your questions. I'm not going to spend time on stuff you don't have questions about. And then I thought we would take a quick look through the take-home final exam assignment, make sure I clarify any of my convoluted phrases, and then answer any other questions you have. I think the grader is going to make a guest appearance to talk to you about any questions you have about grading. Told her to wear her rotten fruit apron and splash shield. So she's going to be here in about 25 minutes. And there is no rule against us quitting early today, right? Have you got enough for your tuition dollar? Okay, so good. If not, just spend more time on the take-home. Do you guys have any questions about the part of the homework assignment you just turned in? Which part? Okay. So there's this formula that I gave you, which you can actually derive if you want to. It's basically a way of making sure we have a signal that's going through our system that looks something like this. And this time constant here, tau bind, is 10 seconds. This one, tau release, is 2 seconds. And we want to take this and we want to put it through a low-pass filter. And we don't want to mess it up too much, okay? We don't want to distort it too much. You're probably used to thinking about things in the frequency domain, right? So if I have a frequency, I need to have a certain h of f so that it's the 3 dB frequency over here is high enough that I don't mess up my signals going through that. Here, instead of thinking about it in terms of frequency, we're thinking about it in terms of the time constants of this rise and fall. And so I'm just I'm telling you that in order for there to only be a 1% error, and VC here is the output, since this is across the capacitor, I'm saying I don't want the output to be more than 1% different than the input. That's really all the left-hand side of this thing is saying, okay? And I'm giving you the expression for what it's equal to. It's equal to this expression here, where tau in is whatever the lifetime is that's going into it, okay? So you guys have seen, I hope, you've put a square wave on an RC filter before, and you've seen what it does at the output. At the output, if I put a square wave in, I get something that rises and then falls and then rises and falls. Okay. And so it's clearly messing up a square wave. The filter is clearly distorting the square wave. Will it distort this? Well, it depends on how close it is to a square wave. If you had to guess which edge would be more likely to get distorted, would it be this edge or this edge? Okay. This edge is slower. It looks more kind of like a slow edge coming out in response to a sharp rise anyway. So it's actually the sharper the edge, the greater the distortion to it will be. So for example, if I had a filter that did this to a square wave, so if a square wave generates this, and I put in a triangle wave that looked like this, the output from the triangle wave would probably look pretty close to what went into it, because these are slow transitions in it. They're low frequencies. This has more high frequencies in it. This edge has more high frequency content than this edge does in it. So actually this one is the one that's more likely to be distorted. It's the faster, more rapidly changing signal. So if I want to make sure that my filter handles both edges, the one that's going to be more of a limit in terms of how small I can make the bandwidth of this filter is going to be the faster one. So when I do this calculation here, I want to use tau is 2 seconds instead of using tau is 10 seconds. Is that all right so far? Kunal, do you have a question about that?
Yeah, I mean, I was just wondering, the question says that you need to consider the maximum value of
Right. We are trying to figure out what value to set RC, and it has to be, we want to find out how to make it big enough.
So will it not, like, when you consider tau in as 10 seconds, then you calculate the value of RC?
You know, let's do it with both. Let's do the calculation with both and see what we end up with, okay? So let's do it with the 2 seconds. 0.1, 0.01 on the left-hand side equals 1 over the absolute value of 1 minus tau n over RC. And now I'm going to say that tau n, in fact, I'm going to solve this whole thing so that I don't have to solve it twice. I'm just going to invert it. So that tells me that I need 1 minus tau n over RC equal to 100. And that, assuming both of these are positive numbers, that means that I need tau n over RC to equal 101. Is that all right so far? Okay. And so now, if I put tau n is equal to the faster one, tau release equals 2 seconds, that tells me that RC is going to be equal to, and if I've messed this up already, you have to stop me before I'm embarrassed. "202 seconds. Is that what I got? Oh, I'm sorry, these are not seconds. Okay, let me just carefully work through this here. Yeah, I messed it up. It's not RC equals 202, it's RC equals tau n over 101. That's what it is. Okay. So if I plug in 2 seconds divided by 101, I get about 0.02 seconds for what RC is. If I had plugged in the other value of tau n equals tau bind equals 10 seconds, I would have got that RC was equal to 0.10 seconds, something like that. Okay, so if I'm going to choose this value or this value, and I don't want to distort either edge, which one do I choose? Do I choose the one that's going to correspond to a 3 dB frequency of I think this one ends up being 2.5 approximately hertz, and this one ends up being 3 dB of 12.5 hertz. Okay? Which one do I choose if I want to make sure that both of these things go through with minimal distortion? I choose the bigger one. I choose the 12.5 hertz one, so that both edges go through without being distorted. I think one issue, and I'll have to go back and look on the assignment, I understand the words minimum and maximum and things like minimum average value were confusing. The trouble is I needed a word to describe noiseless, and so average I sometimes used as noiseless. And I'm going a little bit off tangent, Kunal, here. So I understand that these words about maximum and how I choose to talk about maximum, in part, what I want you guys to get past thinking of is in thinking of everything as an equality. I have an equation, I put in a number, I solve for a value. I want you to think beyond equalities as to which side of the equality works. And in this particular case, the side of the quality is that this is the biggest value. These two would determine the biggest value we would want for RC, okay? And that this is a more stringent limit on RC than this is, and therefore this is the limit that we're going to apply. If I said you have to drive a truck under a bridge that's 7 foot tall and 13 foot tall, you wouldn't design a truck that's 12 foot tall. You want it to meet both criteria. Jacob?
So I guess out of curiosity, I know this is a question, but why wouldn't you subtract the one to add it? You have the absolute value of 1 minus tau.
Yeah.
over RC.
This is a negative quantity because this is going to end up being bigger than 1. And so if this is a negative quantity, when I take the absolute values off, I have to do this. So what that gives me then, if I just do the algebra, so I have a -1 here, I'm going to add 1 to both sides. So I've added a 1 to this side and a 1 to that side, and so I get it to be 101.
So how, I guess, just how from the original question are you supposed to know that that's supposed to be?
I think you can think back to what's going on in terms of the notion of frequencies. So the only case that this would be a positive value is if tau n was less than RC. So if I have an RC filter that has a time constant of 3 seconds, or 2 seconds or whatever, and I run an edge through it that has the exact same time constant, do you think there's going to be much distortion to it? And maybe you don't have the intuition on that, but the answer is yeah, there's going to be a significant amount of distortion to it. It's kind of like running a filter right at the edge, where at the edge of a 3 dB filter, is there going to be any distortion to the waveform? Yeah, there's 3 dB worth of distortion right at the edge of it. And so that's why you wouldn't want to run a filter where tau n is less than RC. In fact, RC needs to be much less than tau n to make this to work. And that's why the absolute value signs appeared here. Yeah, Kanal?
The assignment that I have, it says like determine maximum value of RC. So when I just follow that,
There's a possibility that what I ended up posting was, so after all these discussions in class, what I do is I go back and I edit the assignment for the following year, and there's a possibility that I didn't get the updated version posted. So tell me, I'm going to stare at this while you read to me. What does your assignment say?
it says determine maximum value of RC and the corresponding noise equivalent bandwidth.
Okay. So I would say the maximum value of RC, the biggest that RC can be, is this. It can't be this. Just because this number's bigger than this number doesn't mean that this is the maximum. In fact, it can't be this big, or else it screws up the falling edge. But I understood that wording was potentially a little confusing, because if you just read and go, okay, I'm going to compare two values of RC and I need the maximum, I'm going to take the bigger one, without thinking through what the impact is. And that's why I got rid of the word maximum when I reworded it, that I apparently didn't share with you. So I apologize, I didn't give you the updated version of it. And look, I will ask the grader to be lenient on this. There'll be a point or two for that. But if you use a bandwidth of 2.5 hertz all the way through the problem, we won't continue to take off points for all the other parts, okay? Is there another question, Ash?
Yeah, so when you said the tau binding is 10 seconds, tau releasing is 2 seconds.
Yeah.
So you want the whole time, right?
Yeah, I want both of those features. I want that whole curve to be able to go through the RC filter with minimal distortion.
So why wouldn't you take it to be 12 seconds?
Well, these times are not the duration of something. If you remember, this point out here is like at 120 seconds, right? They're not the duration, they're the characteristic. It's kind of like if I said I wanted a 100 hertz signal and a 20 hertz signal to go through a filter, I wouldn't say, okay, I need a 120 hertz filter by adding them together. And it's kind of the same notion here. You wouldn't add the taus together for them to go through. Only one of the taus at a time is in play. Any other questions about this part? Any other questions about any other part of the assignment? The maximum SNR, can you give, do you know, were you referring to part D or so forth of this problem? Okay. So, when you guys did the calculation without the filter on it, and again, remember that I changed a number in my problem. I changed my C to 10 to the 12 up here someplace. C equilibrium to 10 to the 12. If you did the problem with 10 to the 9, that's fine, and it'll be graded as if that's fine. So that will have some impact. But when I went through it, I got a signal-to-noise ratio from the first part that was 1.6 million. Okay, 1.6 times 10 to the 6. Then I choose a filter bandwidth for the second part, and based on the filter bandwidth I chose of 12.6, what I found out was that the change in delta F was a factor of 792. So that this new filter was 792 times narrower than 10 kilohertz I had before. And shot noise gets multiplied by delta F. Thermal noise gets multiplied by delta F. And amplifier noise, since it's proportional to thermal noise, gets multiplied by delta F. So all of the noise sources are scaling as delta F in this case. All right? And because they're all scaling as delta F, and I've knocked the noise down by making the bandwidth smaller, that means the signal-to-noise ratio should go up, right? And so the signal-to-noise ratio goes up by that same factor of 792, and so this is the number I get then, 1 billion something for the signal-to-noise ratio. Okay? Enormous signal-to-noise ratios. So when we go on now to figure out what the concentration is we need for a signal-to-noise ratio of 9, K is 3 and I square it to get 9, then I'm going to have a lower number than that. And I'll just show you that when I work through that, part of it is that, so concentration is proportional to this IPD here, except for a dark current. Actually, if it's just the photo current, IPD is proportional to C. So there's a term for the signal magnitude that comes in that's proportional to C squared, or in this case, IPD squared. But down here in the noise for shot noise, this stuff isn't changing, but the shot noise is changing because IPD is changing because the concentration is changing. The average current there is changing. And as a result, shot noise changes. So I have a constant 9 equal to something proportional to C squared in the numerator divided by something with a term proportional to C in the denominator. So when I rearrange those terms, I'm going to have an equation that has constant terms, C squared terms, and terms proportional to C. So I'm going to end up with a quadratic equation that I have to solve for C. And when I go through and solve that, the number I get here is that instead of having 10 to the 12th molecules, if I have 5 times 10 to the 7th molecules, then I will have just be right at the limit of detection. So 5 times 10 to the 7 molecules would be my limit of, per square millimeter would be my limit of detection. Did that answer your question? Okay. And again, so just if you use the other bandwidth, then obviously that number will be off. We'll figure out what the correct answer is for a bandwidth of 2.5, and we won't tick points off all the way down the problem. When Madeline walks in at 11:30, remind me that I said that, okay? Yeah, Tom?
I just had a question. Are we going to be able to talk to her about the grading on this homework?
Sure. You can talk to her about the grading on all the homeworks. There's been some discussion. I think she wants to talk about the table that you guys created on homework number 2. And I've talked to her some about the grading on that. I think we're going to give a few points back on the table there. It turns out that you guys, some of you, when you were calculating the standard deviation of the raindrop FFT, you decided to divide by 1,024 before you took the standard deviation of the FFT. And I'm not sure why you did that, but that shouldn't be an enormous point loss as a result of doing that. And so that's going to get corrected. All right?
For this question here, why did you not, on the bottom of it, since you are calculating like the signal-to-noise ratio, why did you not also include the thermal noise? You just did like the amplifier?
This is actually plus
Oh, that's
thermal.
plus. Oh, okay. Okay.
Yeah. So that's, I just put the two of them together. This would be 2 times just V thermal here.
Can you go back to question 1?
Uh-huh.
Question for
Mm-hmm.
It's short noise plus thermal plus
Shot noise plus amplifier noise plus thermal noise. So if you look back up here, I said, I know thermal noise. Amplifier plus thermal noise is just going to be thermal noise times whatever 3 dB is. So basically 2 times the thermal noise. All right? Okay. Any other questions on, yeah, Gitesh?
So going back to this rise time and fall time,
Mm-hmm.
the bigger the bandwidth, the better.
The bigger the bandwidth, the less it will distort your signal.
So, but our if you go by our noise thing,
Uh-huh.
lesser the bandwidth, then it's better. Right?
That's right. Engineering is about trade-offs.
Yeah. So what I'm saying is now, how about design in which we have a smaller bandwidth filter and we sweep across it, right? To the 2.5 hertz filter, we sweep across time so that we get less noise as well as we don't distort it.
Are you saying that the RC value of the filter is changing in time?
Change it.
Okay, well, that's a pretty sophisticated system you're building. You're building an adaptive filter. And I did not contemplate that. Did you actually go through and solve for an R as a function of time or C as a function of time?
I'm just thinking because of I see the two values and I see trade-offs. And when trade-offs comes to mind, I think of something.
Sure.
Some solution.
And I guess if in general you knew whenever, and usually what happens over here is you're flowing a rinse through the system, you're knocking molecules out of it to kind of clean it up and just leave the bound molecules. And so you could design a system, and I like your out-of-the-box thinking, you could design a system that sensed when the valve was changed, and it could just switch to a different filter and generate less noise on that part. Maybe you should go patent that. That sounds like that's more sophisticated than what's typically done in this type of instrumentation. The SNR would be proportional to what?
The RC time constant. That case, that would be.
You're right. You'd kind of have a different noise level for falling than you would have for rising, and you'd have different, in terms of analysis, you'd have different signal to noise ratios. The only thing I would say about what you said is signal to noise ratio is actually inversely proportional to RC. It's not proportional to RC. Oh, wait, it is. I'm sorry, you're absolutely right. Signal noise ratio is proportional to RC. Right, okay. All right, anything else about that before we take a look at the take-home? Take-home has been posted. And so, what the main key of the take-home is I want you to do, this is mostly MATLAB, and I want you to look at the same basic setup, but I want you to do it in the presence of flicker noise now. Okay? So, you're going to use the values that you got from the last homework for C of t, same kind of two-part rise and fall, but now we're going to assume we have an equilibrium concentration of 10 to the 9th on it. So we would not expect to see nearly as big of signals as you had in the first part of the last problem, okay? I'm telling you a specific value of RC to use, and I'm telling you to model this with 2 to the 15th points. So your vectors now, instead of having however many you had last time, they're going to have 32,000 points in your vector. I have run this in MATLAB on my teeny little machine. It did not melt down, so you should be fine. And we're going to model that for that same time. Remember, it's kind of rising for 120 seconds, and then it falls. We're going to model that thing for a total of 163.835 seconds. And to make that work out, the sample time between points on this first part is 5 milliseconds. Okay? And basically, most of this is, I want you to produce a plot that's just the signal, and then a time version of it that's signal plus shot noise, and then a time version of it that's signal plus shot noise plus thermal and amplifier noise, and finally one that's signal plus shot noise plus thermal and amplifier noise plus flicker noise. Okay? And in order to do this, you're going to need to be able to add noise to it, but the noise that you have needs to be filtered. Okay? When you add noise to it, it's going to be filtered noise. And to save you some hassle, I'm helping you go through and create a filtered noise vector, basically, that you can use for any form of white filtered noise. And so that's what this first part is about. And I'm showing you a numerically efficient way to create filtered noise. And don't say anything specific about it, because part of the question is I want you to explain to me why I chose this code to model filtered noise. And so I am creating this function, whose name should hopefully be suggestive to you. And I am using this operation right here of that vector with my random white noise matrix to create filtered noise. And I want you to explain to me why I'm doing this to create filtered noise. Okay. And then I want you to create a Bode plot type of spectrum. Is anybody doing this in anything other than MATLAB? Good. I think it's probably going to be easier in MATLAB. You guys know about the log plot function. So instead of PLOT, open parent, stuff things inside, there's LOG open parent, stuff things inside to produce a log plot like a Bode plot. Is anybody unfamiliar with the term Bode plot, B-O-D-E plot? Everybody knows what a Bode plot is. Okay. Kunal, did you have another question?
I was actually doing it in
Okay. Python is fine. I'm wanting you to use the random generating function that has a normal distribution to it as opposed to a uniform distribution. So this one doesn't go between 0 and 1. It goes both directions, and it creates a Gaussian type of distribution that has a 0 average and has a standard deviation of 1. Okay? A couple places in this assignment, I say I want you to scale the noise to make it so big. And what that means is I want you to multiply through the entire noise array by some scalar multiplier to make the noise bigger, more amplitude, or smaller. It doesn't mean messing differently with different time points. It just means multiplying. Now, in one case, you might multiply a portion of the time differently than another portion of the time, but I'll let you figure out where that is, okay? So I want you to create this noise vector, and if you're going to reuse the noise, the same noise vector, for more than one type of noise. Let's say you want to use it for shot noise and you want to use it for amplifier and thermal noise. Those two noises should not be correlated with each other. They should be, so the amplifier thermal noise is uncorrelated with the shot noise. So if you want to add these voltages, these voltage noises together for each one of those and reuse the same noise, you can't use it in exactly the same point of the noise vector. So what I'm saying is for the noise vector to take the noise vector that's 32,700 something points long and shift it by 5,000, take the 5,000 that fell out the end and put it back in this end over here. That's a circular shift. And the MATLAB function that does the circular shift is called W shift, okay? And use a shifted one for thermal and amplifier, for example, and the unshifted one for the shot noise, all of course appropriately scaled, so that those noises are uncorrelated. And the idea is that this thing is so random that after 5,000 values, it's not going to be correlated with what it started with at all, okay? As you guys know from the autocorrelation, right? You shift the noise streams a lot and that they're no longer correlated. Any questions about that, what I've just talked about? Okay? The next thing is I want you to generate flicker noise. You previously on an assignment generated flicker noise with 2 levels, and it did not have an average value of 0. It was jumping between 0 and 1, so the average was not 0. I want you to now generate a 3-level flicker noise sequence that does have an average of 0. And to do that, I'm going to have you generate the 2-level sequence that just like you did before, except I want it to hop back and forth between -1 and +1. And I'm going to have you take 2 of those and add them together, okay? For us to get flicker noise right, we have to make sure that we know how long probabilistically the system will be in one state before it flips to another state. So the probability I want you to use on this part of the problem when the sampling time is 5 milliseconds is 0.2. Yeah, Zenon?
When you say take 2 of them and add them together, do you generate a sequence of 32,000 and another one and add those 2 sequences together? Or?
Okay. After you've generated the 2-level state switching sequence, one of them from this part up here, generate the 3-level state switching sequence of the same length by adding a copy of the first one. So take the exact thing you've made, but now, just like before, I want you to shift it by 10,000 elements before you add it back to itself. And that 10,000, again, will cause those sequences to be, the two-level ones to be decorrelated.
So just tack it onto the end of one.
No.
Could you essentially just create another random variables between -1 and 1 and then add those to the other 2?
You could if you wanted to. I'm just trying to save you redundant code. And teach you a little trick, I guess, about how to check on, think about correlations on things. Here's what one sequence looks like. For example, and I'm just saying, you can take that same sequence and you can shift it over. So I'm going to try to duplicate what I drew there, just shifted. and add these two together, but whatever got shifted out past the end of this one, we're going to take and we're going to paste on over here. Circular shift it. Does that make sense?
Yeah.
Okay. So importantly here, the expected duration in the two-level sequences before there's a state change is 25 milliseconds. Why is that? Because the probability of switching is 20% in each and every time instant. And the time sample here is 5 milliseconds. So every time interval of 5 milliseconds, there's a 20% chance of switching. So on average, hey, Madeline, come on in. On average, it's going to take 25 milliseconds for us to, when we multiply those two together, to have the expected value of a change. Okay? Madeline, let me just finish up with this part, and then you're welcome to talk to class. So I've generated the 3-level by adding those two together. And then there's some stuff here about scaling the size of the flicker noise. And it gets a little dicey as to whether we scale it before we put it through our filters or after we put it through our filters. So in particular for this flicker noise, I want you to scale it before you stick it through the filters. Okay? Now, once we have these noise things figured out, this flicker noise was the last one we're adding. So we're going to take the previous part E, which should have had shot noise and thermal noise, but now you're going to add in flicker noise. And you're going to give me a time plot to show me what that looks like as a function of time with the noise added in. And then I want you to just look at that plot or analyze it if you prefer. I want you to tell me what the magnitude of the signal is in volts. And I want you to tell me, I want you to do an analysis of the noise in it total, with all those types of noise added up. I want to know what the root mean square value for the noise is between 50 and 100 seconds. And then I want you to tell me what the signal to noise ratio is if we include all those forms of noise. All right? I think you will find flicker noise will be pretty significant in this problem, okay? But don't fear, we have a way of getting rid of it.
So when you're going, I guess, a little bit step back, you're going from -1 to 1 as well, and you have the probability of 0.2. So before we did if it's less than that 0.2 value.
Right.
So in this case, wouldn't there be a lot more that's going to be less since we're going to be going into the negative numbers as well? So you wouldn't have like an even distribution.
Good question. This is, remember, this is state switching.
Oh, okay.
So every time I say, do I change, do I change, do I change, and only if that uniformly distributed random value, don't use rand in there, you just use rand, is less than p, only then do I have a state change. Once I'm in that, I'm in the new state. Let me just write out some MATLAB code that, because I think a few of you may have struggled, and by the way, there's a note in here that if you didn't get the two-state problem right, that's the one thing I'm going to let you copy off of somebody else during this take-home exam. Okay, you can go ask another student for that, or I'll show you something right here. You cannot talk to students about anything else, and I'd prefer if you're going to talk to each other about anything else, I'm going to prefer that if you're going to ask somebody for their code for that, you send them an email message and say, please give me your code for the two-state solution, and that's all I want you to send, okay, for that homework. And just to highlight this, I want to emphasize the rules for this assignment that are underlined here. You cannot discuss this with anybody else that's enrolled in this class, okay? You can talk about it with me. I'm available 1:30 to 2:30 today and Tuesday and Thursday next week. You can go talk with other professors. Go buy Ali Pazeshki a beer and get him to do your take-home final for you, just as long as you tell him it's a take-home final, okay? And you cannot exchange anything of value except for the tuition you've already paid, okay, in order to do this. So no, absolutely serious, no paying somebody to do this work for you, obviously. I guess it depends on what type of beer, is whether it's of value or not. Yeah, there you go. Yeah. All right. Sorry, may have been some slight contradiction of my rules in suggesting you go buy Pizeski a beer. Go get Pizeski some air. Where were we? Oh, I was going to show you some code for the two-state. Here's the code that I would probably use to generate the two-state. And then I have a quiz. Then I have a question for you, a coding question. I'd say something like flick for flicker noise equals zeros. Have you guys noticed that MATLAB spells zeros incorrectly? I keep spelling it correctly and I keep getting it flagged wrong. Because, oh. Yeah, I do that all the time. Yeah. Right.
Also, two bits.
There are?
Yeah, one is a third.
But isn't the plural of zero no possessives, just the plural of it? Isn't that correct?
I mean, I knew that there were two, but it says the third person present zeros with an E.
God. I didn't realize in English that we applied tense to any nouns. So okay, I think I've got that right, that will generate that sequence up there.
And your randoms are still between 0 and 1.
Right, this function in MATLAB, uniform distribution between 0 and 1. Do not use rand_in here. Do use rand_in when I ask you to. Since everything ends up being a 1 or a -1, what's the point of this? Isn't that a waste? Isn't this an unneeded statement?
You need to identify the size.
Turns out technically you don't, but it makes the code, you're right. This just makes the code run faster. That's the only thing that does for you.
And I also read more in zeros with an E. But these zeros.
Oh, really?
Yeah.
I didn't know that.
Yeah.
The things I learned by teaching, this is cool. All right, I'm going to go use zeros correctly from now on. Huh, okay. Any other questions so far about what we've talked about in this? For the flicker sequence, that's correct. Correct. Yes. Let me not complicate that answer. Yes. Oh, I'm lying. No. That's not true, and here's why. When tau sub s, the sample time, equals 5 milliseconds, we're going to use p equals 0.2. Stay tuned. Okay? By the way, if somebody hits something where they think I messed something up, the p-value that I messed something up is not 0, okay? So if you think I messed something up, come talk to me. Don't stew and fret and lose all sleep. Just come talk to me. Okay, I think that's the end of it, of that part. Yeah, Jacob?
It says in that part
Uh-huh.
it says plot the first 1,000 points of your 3-level sequence to make sure it is jumping between -2, 0 and +2.
The 3-level sequence.
Right.
So-
never mind. Since we're adding it to the other one, I guess that makes sense.
So your possibilities are you can have 1 + 1, 1 - 1, -1 + 1, and -1 - 1. So It should be jumping between those. And that was really just, I want to give you guys a little bit of guidance so you don't give me complete garbage on this exercise. So it's just kind of a check that you're doing things right. This is generating the 2-level sequence, not the 3-level sequence. Shall I go on to the final problem? Okay, here's what we're going to do now is flicker noise is going to be bad, and we're going to try to see how much of it we can get rid of. So I want you to now assume that instead of P excitation being constantly on at 10 milliwatts, that you're taking it and you're turning it on, and then off, and then on, and then off, and then on, and then off, going between 0 milliwatts and 10 milliwatts, back and forth, according with 50% duty cycle, like a square wave with 50% duty cycle. Okay? So that's what this part up here is talking about. And the frequency, as I said, is at 10 kilohertz. You no longer want to low-pass filter this thing because the 10 kilohertz isn't going to get through your low-pass filter. You need to band-pass filter it. And so I'm telling you to band-pass filter it about this 10 kilohertz with a total of 40 hertz above and 40 hertz below that frequency for the bandpass. Okay? And you are going to figure out what kind of bandpass filter you're going to use to accomplish that. It has to meet the 3 dB spec, and you should shape the filter to avoid ringing. Okay? Now that we have signals going, let me finish just this part and I'll come talk to you, Jacob. Now that we have signals going much faster, we can't live with a 5 millisecond sampling time anymore, or else we're going to completely miss these transitions. So you have to greatly decrease the sampling time to 20 microseconds. Now, if I kept the same total time duration, you would have 2 to the 15 plus 11, you'd have 2 to the 26 points in your vector. Let's not do that, okay? So instead, we're going to focus in and we're just going to look at a very short, about a half-second window in what's going on to analyze it. So we're just looking at that short time frame. Jacob?
What exactly do you mean by shape?
That is a great thing for you to figure out. Okay? You might, if I recorded it, you might find something in a prior video for this class about that. Any other questions about this point so far? All right. Now what we want to do is we want to assume a noiseless system here in part A, and I want you to run it through your bandpass filter with no noise. I just want you to see what your filter does to this on-off pulses of voltage coming through, okay? I want you to create, just as you did before, a 3-level flicker noise system, the same magnitude you had before, with the same expected state change time, okay? And so now we're not doing 5 milliseconds anymore, we're doing 20 microseconds. And you, I don't think I tell it to you, I think you need to figure out a new p-value in order to make sure that the expected intervals, and expected, obviously this is random, right? So don't look at your thing and say, oh, why didn't it change at exactly 25 milliseconds? But on average, the state change is occurring at that rate. You're going to have to figure out what p-value you're going to use for that. And then I want you to plot just the flicker noise. No signal at all, just the flicker noise. And I want you to plot it without any filtering. I want you to plot your flicker noise with the same low-pass bandwidth that should give you an idea of what happened in the previous problem. And I want you to plot what's happening to that flicker noise with a bandpass filter. Okay? And then I want you to plot the frequency spectrum just from the last one, just from the bandpass. I want to see what your frequency spectrum of your noise, of just flicker noise coming through your bandpass filter looks like. Almost done. Only 5 more hours of work. Part A was the signal only, no noise. So now I want to go back and I want you to plot the voltage output with shot noise plus the signal. I then want you to plot the output with not only shot noise but thermal noise added in. So notice that this refers to this one, repeating D, okay? Then I want you to do this previous one with thermal and shot noise but also add flicker noise in. That's what refers to part E. One sentence, I want you to tell me what effect the dark current has on your results you observe here in F. Kind of similar questions before. What's the RMS value of the output voltage, which is going to be like your signal? And if you'd analyze the output, and then I want you to think about that. And this is not a calculate. This is more a think and draw. Okay, that part. What's the noise? What's the new signal to noise ratio? We hope, and you guys are going to prove, see if I got this right or not, we hope the signal to noise ratio will be better with problem 4 than it was with problem 3. Last thing, extra credit for those of you who like to write. Write me one correctly structured, grammatically correct paragraph. Well-structured means use a topic sentence at the first line of the paragraph that properly describes what's in the paragraph. And anything else, you know about the Writing Center. You can always take these things to the Writing Center. Tell me what you got out of this exercise. All right? Don't make it acerbic. You've already written that on all your course reviews. So, any questions about your take-home exam? If not, I thank you for taking this class. I've had fun. I hope you guys have got something out of it. Is there anybody in here who did not learn more about noise from this class than any other class they've taken at CSU? Anybody learn more about noise from some other class you've taken at CSU? Good. I've taught you something. All right. Please make use of my office hours. I got this to you as early as I could, and we talked about it today so you'd start on it early and you wouldn't come to me with questions at 10 p.m. next Thursday when I won't answer them anyway because I'll finally be asleep. Jacob? It is. I'm giving you an extra day.
So is it Thursday at 11?
Correct. Just before midnight. Yep. I have it ready to go. I will actually just do that now. You can watch me mess around Canvas as soon as we're done. All right? So thanks, guys. Had fun with class. Hope you enjoyed it.